In computer science, a linked list is a data structure consisting of a group of nodes which together represent a sequence. Under the simplest form, each node is composed of a data and a reference to the next node in the sequence. More complex variants add additional links. This structure allows for efficient insertion or removal of elements from any position in the sequence. Linked lists are among the simplest and most common data structures. They can be used to implement several other common abstract data types, including lists, stacks, queues, associative arrays, and S-expressions, though it is not uncommon to implement the other data structures directly without using a list as the basis of implementation. The principal benefit of a linked list over a conventional array is that the list elements can easily be inserted or removed without reallocation or reorganization of the entire structure because the data items need not be stored contiguously in memory or on disk. Linked lists allow insertion and removal of nodes at any point in the list, and can do so with a constant number of operations if the link previous to the link being added or removed is maintained during list traversal. On the other hand, simple linked lists by themselves do not allow random access to the data, or any form of efficient indexing. Thus, many basic operations such as obtaining the last node of the list, or finding a node that contains a given datum, or locating the place where a new node should be inserted may require scanning most or all of the list elements. The advantages and disadvantages of using linked lists are as follows. Advantages: linked lists are a dynamic data structure, allocating the needed memory when the program is initiated. Insertion and deletion node operations are easily implemented in a linked list. Linear data structures such as stacks and queues are easily executed with a linked list. They can reduce access time and may expand in real time without memory overhead. Disadvantages: they have a tendency to waste memory due to pointers requiring extra storage space. Nodes in a linked list must be read in order from the beginning as linked lists are inherently sequential access. Nodes are stored incontiguously, greatly increasing the time required to access individual elements within the list. Difficulties arise in linked lists when it comes to reverse traversing. Singly linked lists are extremely difficult to navigate backwards, and while doubly linked lists are somewhat easier to read, memory is wasted in allocating space for a back pointer. History: linked lists were developed in 1955–1956 by Alan Newell, Cliff Shaw and Herbert A. Simon at Rand Corporation as the primary data structure for their information processing language. IPL was used by the authors to develop several early artificial intelligence programs, including the logic theory machine, the general problem solver, and a computer chess program. Reports on their work appeared in IRE Transactions on Information Theory in 1956, and several conference proceedings from 1957 to 1959, including proceedings at the Western Joint Computer Conference in 1957 and 1958, and information processing in 1959. The now classic diagram consisting of blocks representing list nodes with arrows pointing to successive list nodes appears in Programming the Logic Theory Machine by Newell and Shaw in Proc. WJCC, February 1957. Newell and Simon were recognized with the ACM Turing Award in 1975 for having made basic contributions to artificial intelligence, the psychology of human cognition, and list processing. The problem of machine translation for natural language processing led Victor Invid Massachusetts Institute of Technology to use linked lists as data structures in his COMIT programming language for computer research in the field of linguistics. A report on this language entitled A Programming Language for Mechanical Translation appeared in Mechanical Translation in 1958. Lisp, standing for List Processor, was created by John McCarthy in 1958 while he was at MIT, and in 1960 he published its design in a paper in the Communications of the ACM, entitled Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. One of Lisp's major data structures is the linked list. By the early 1960s, the utility of both linked lists and languages which use these structures as their primary data representation was well established. Bert Green of the MIT Lincoln Laboratory published a review article entitled Computer Languages for Symbol Manipulation in IRE Transactions on Human Factors in Electronics in March 1961, which summarized the advantages of the linked list approach. A later review article, A Comparison of List Processing Computer Languages by Bobrow and Raphael, appeared in Communications of the ACM in April 1964. Several operating systems developed by technical systems consultants use singly linked lists as file structures. A directory entry pointed to the first sector of a file, and succeeding portions of the file were located by traversing pointers. Systems using this technique included Flex, Mini-Flex, and Flex9. A variant developed by TSC and marketed by Smoke Signal Broadcasting in California, used doubly linked lists in the same manner. The TSS-360 operating system, developed by IBM for the System 360/370 machines, used a double-linked list for their file system catalog. The directory structure was similar to Unix, where a directory could contain files and/or other directories and extend to any depth. A utility FLE was created to fix file system problems after a crash, since modified portions of the file catalog were sometimes in memory when a crash occurred. Problems were detected by comparing the forward and backward links for consistency. If a forward link was corrupt, then if a backward link to the infected node was found, the forward link was set to the node with the backward link. A humorous comment in the source code where this utility was invoked stated, "Everyone knows a flea collar gets rid of bugs in cats." Basic concepts and nomenclature. Each record of a linked list is often called an element or node. The field of each node that contains the address of the next node is usually called the next link or next pointer. The remaining fields are known as the data, information, value, cargo, or payload fields. The head of a list is its first node. The tail of a list may refer either to the rest of the list after the head, or to the last node in the list. In Lisp and some derived languages, the next node may be called the CDR of the list, while the payload of the head node may be called the CAR. Singly linked list. Singly linked lists contain nodes which have a data field as well as a next field, which points to the next node in line of nodes. Doubly linked list. In a doubly linked list, each node contains, besides the next node link, a second link field pointing to the previous node in the sequence. The two links may be called forward, S, and backwards, or next and previous. A technique known as XOR linking allows a doubly linked list to be implemented using a single link field in each node. However, this technique requires the ability to do bit operations on addresses, and therefore may not be available in some high-level languages. Multiply linked list. In a multiply linked list, each node contains two or more link fields, each field being used to connect the same set of data records in a different order. While doubly linked lists can be seen as special cases of multiply linked list, the fact that the two orders are opposite to each other leads to simpler and more efficient algorithms, so they are usually treated as a separate case. Circular list. In the last node of a list, the link field often contains a null reference, a special value used to indicate the lack of further nodes. A less common convention is to make it point to the first node of a list. In that case, the list is said to be circular or circularly linked. Otherwise it is said to be open or linear. In the case of a circular doubly linked list, the only change that occurs is that the end, or tail, of the said list is linked back to the front, or head, of the list and vice versa. Sentinel nodes. In some implementations, an extra sentinel or dummy node may be added before the first data record and/or after the last one. This convention simplifies and accelerates some list handling algorithms, by ensuring that all links can be safely dereferenced and that every list always has a first and last node. Empty lists. An empty list is a list that contains no data records. This is usually the same as saying that it has 0 nodes. If sentinel nodes are being used, the list is usually said to be empty when it has only sentinel nodes. Hash linking. The link fields need not be physically part of the nodes. If the data records are stored in an array and referenced by their indices, The link field may be stored in a separate array with the same indices as the data records. List handles. Since a reference to the first node gives access to the whole list, that reference is often called the address, pointer, or handle of the list. Algorithms that manipulate linked lists usually get such handles to the input lists and return the handles to the resulting lists. In fact, in the context of such algorithms, the word list often means list handle. In some situations, however, it may be convenient to refer to a list by a handle that consists of two links, pointing to its first and last nodes. Combining alternatives. The alternatives listed above may be arbitrarily combined in almost every way, so one may have circular doubly linked lists without sentinels, circular singly linked lists with sentinels, etc. Trade-offs. As with most choices in computer programming and design, no method is well suited to all circumstances. A linked list data structure might work well in one case, but cause problems in another. This is a list of some of the common trade-offs involving linked list structures. Linked lists versus dynamic arrays. A dynamic array is a data structure that allocates all elements contiguously in memory, and keeps account of the current number of elements. If the space reserved for the dynamic array is exceeded, it is reallocated and copied, an expensive operation. Linked lists have several advantages over dynamic arrays. Insertion or deletion of an element at a specific point of a list, assuming that we have indexed a pointer to the node already, is a constant time operation, whereas insertion in a dynamic array at random locations will require moving half of the elements on average, and all the elements in the worst case. While one can delete an element from an array in constant time by somehow marking its slot as vacant, this causes fragmentation that impedes the performance of iteration. Moreover, arbitrarily many elements may be inserted into a linked list, limited only by the total memory available. While a dynamic array will eventually fill up its underlying array data structure and will have to relocate an expensive operation, one that may not even be possible if memory is fragmented, although the cost of reallocation can be averaged over insertions, and the cost of an insertion due to reallocation would still be amortized. 1. This helps with appending elements at the array's end, but inserting into middle positions still carries prohibitive costs due to data moving to maintain contiguity. An array from which many elements are removed may also have to be resized in order to avoid wasting too much space. On the other hand, dynamic arrays allow constant-time random access, while linked lists allow only sequential access to elements. Singly linked lists, in fact, can be easily traversed in only one direction. This makes linked lists unsuitable for applications where it's useful to look up an element by its index quickly, such as heap sort. Sequential access on arrays in dynamic arrays is also faster than on linked lists on many machines, because they have optimal locality of reference and thus make good use of data caching. Another disadvantage of linked lists is the extra storage needed for references, which often makes them impractical for lists of small data items such as characters or Boolean values, because the storage overhead for the links may exceed by a factor of 2 or more the size of the data. In contrast, a dynamic array requires only the space for the data itself. It can also be slow, and with an array allocator, wasteful, to allocate memory separately for each new element, a problem generally solved using memory pools. Some hybrid solutions try to combine the advantages of the two representations. Unrolled linked lists store several elements in each list node, increasing cache performance while decreasing memory overhead for references. CDR coding does both these as well, by replacing references with the actual data referenced, which extends off the end of the referencing record. A good example that highlights the pros and cons of using dynamic arrays versus linked lists is by implementing a program that resolves the Josephus problem. The Josephus problem is an election method that works by having a group of people stand in a circle. Starting at a predetermined person, you count around the circle n times. Once you reach the nth person, take them out of the circle and have the members close the circle. Then count around the circle the same n times and repeat the process, until only one person is left. That person wins the election. This shows the strengths and weaknesses of a linked list versus a dynamic array. because if you view the people as connected nodes in a circular linked list, then it shows how easily the linked list is able to delete nodes. However, the linked list will be poor at finding the next person to remove and will need to search through the list until it finds that person. A dynamic array, on the other hand, will be poor at deleting nodes as it cannot remove one node without individually shifting all the elements up the list by one. However, it is exceptionally easy to find the nth person in the circle by directly referencing them by their position in the array. The list ranking problem concerns the efficient conversion of a linked list representation into an array. Although trivial for a conventional computer, solving this problem by a parallel algorithm is complicated and has been the subject of much research. A balanced tree has similar memory access patterns and space overhead to a linked list while permitting much more efficient indexing, taking O, log n, time instead of O, n, for a random access. However, insertion and deletion operations are more expensive due to the overhead of tree manipulations to maintain balance. Schemes exist for trees to automatically maintain themselves in a balanced state, AVL trees or red-black trees. Singly linked linear lists versus other lists, while doubly linked and/or circular lists have advantages over singly linked linear lists. Linear lists offer some advantages that make them preferable in some situations. A singly linked linear list is a recursive data structure, because it contains a pointer to a smaller object of the same type. For that reason, many operations on singly linked linear lists often have very simple recursive algorithms, much simpler than any solution using iterative commands. While those recursive solutions can be adapted for doubly linked and circularly linked lists, the procedures generally need extra arguments and more complicated base cases. Linear singly linked lists also allow tail sharing, the use of a common final portion of sublist as the terminal portion of two different lists. In particular, if a new node is added at the beginning of a list, the former list remains available as the tail of the new a simple example of a persistent data structure. Again, this is not true with the other variants. A node may never belong to two different circular or doubly linked lists. In particular, Sentinel nodes can be shared among singly linked non-circular lists. The same Sentinel node may be used for every such list. In Lisp, for example, every proper list ends with a link to a special node, denoted by nil or, whose CAR and CDR links point to itself. Thus a Lisp procedure can safely take the CAR or CDR of any list. The advantages of the fancy variants are often limited to the complexity of the algorithms, not in their efficiency. A circular list, in particular, can usually be emulated by a linear list together with two variables that point to the first and last nodes, at no extra cost. Doubly linked versus singly linked, double linked lists require more space per node, and their elementary operations are more expensive. But they are often easier to manipulate because they allow fast and easy sequential access to the list in both directions. In a doubly linked list, one can insert or delete a node in a constant number of operations given only that node's address. To do the same in a singly linked list, one must have the address of the pointer to that node, which is either the handle for the whole list or the link field in the previous node. Some algorithms require access in both directions. On the other hand, doubly linked lists do not allow tail sharing and cannot be used as persistent data structures. Circularly linked versus linearly linked. A circularly linked list may be a natural option to represent arrays that are naturally circular, for example the corners of a polygon, a pool of buffers that are used and released in FIFO order, or a set of processes that should be time-shared in round-robin order. In these applications, a pointer to any node serves as a handle to the whole list. With a circular list, a pointer to the last node gives easy access also to the first node, by following one link. Thus, in applications that require access to both ends of the list, a circular structure allows one to handle the structure by a single pointer, instead of two. A circular list can be split into two circular lists, in constant time, by giving the addresses of the last node of each piece. The operation consists in swapping the contents of the link fields of those two nodes. Applying the same operation to any two nodes in two distinct lists joins the two lists into one. This property greatly simplifies some algorithms and data structures, such as the chord edge and face edge. The simplest representation for an empty circular list is a null pointer, indicating that the list has no nodes. Without this choice, many algorithms have to test for this special case, and handle it separately. By contrast, the use of null to denote an empty linear list is more natural and often creates fewer special cases. Using Sentinel nodes, Sentinel node may simplify certain list operations, by ensuring that the next and/or previous nodes exist for every element, and that even empty lists have at least one node. One may also use a Sentinel node at the end of the list, with an appropriate data field, to eliminate some end-of-list tests. For example, when scanning the list looking for a node with a given value x, setting the Sentinel's data field to x makes it unnecessary to test for end-of-list inside the loop. Another example is the merging two sorted lists. If their Sentinels have data fields set to +a, the choice of the next output node does not need special handling for empty lists. However, Sentinel nodes use up extra space, and they may complicate other operations. However, if the circular list is used merely to simulate a linear list, one may avoid some of this complexity by adding a single Sentinel node to every list, between the last and the first data nodes. With this convention, an empty list consists of the Sentinel node alone, pointing to itself via the next node link. The list handle should then be a pointer to the last data node, before the Sentinel, if the list is not empty. Or to the Sentinel itself, if the list is empty. The same trick can be used to simplify the handling of a doubly linked linear list, by turning it into a circular doubly linked list with a single Sentinel node. However, in this case, the handle should be a single pointer to the dummy node itself. Linked list operations. When manipulating linked lists in place, care must be taken to not use values that you have invalidated in previous assignments. This makes algorithms for inserting or deleting linked list nodes somewhat subtle. This section gives pseudocode for adding or removing nodes from singly, doubly, and circularly linked lists in place. Throughout we will use null to refer to an end-of-list marker or Sentinel, which may be implemented in a number of ways. Linearly linked lists, singly linked lists, our node data structure will have two fields. We also keep a variable first node which always points to the first node in the list, or is null for an empty list. Record node, data. The data being stored in the node next a reference to the next node, null for last node. Record list, node first node points to first node of list. Null for empty list. Traversal of a singly linked list is simple, beginning at the first node and following each next link until we come to the end. Node equals list first node, while node not null. Node equals node next. The following code inserts a node after an existing node in a singly linked list. The diagram shows how it works. Inserting a node before an existing one cannot be done directly. Instead, one must keep track of the previous node and insert a node after it. Function insert after, node new node, insert new node after node, new node next, equals node next equals new node. Inserting at the beginning of the list requires a separate function. This requires updating first node. Function insert beginning. List, node new node, insert node before current first node, new node next equals list first node equals new node. Similarly, we have functions for removing the node after a given node, and for removing a node from the beginning of the list. The diagram demonstrates the former. To find and remove a particular node, one must again keep track of the previous element. Function remove after, node, remove node past this one, obsolete node, equals node next equals node next, destroy obsolete node. Function remove beginning, list, remove first node, obsolete node, equals list first node equals list first node next point past deleted node, destroy obsolete node. Notice that remove beginning sets list first node to null when removing the last node in the list. Since we can't iterate backwards, efficient insert before or remove before operations are not possible. Appending one linked list to another can be inefficient unless a reference to the tail is kept as part of the list structure, because we must traverse the entire first list in order to find the tail, and then append the second list to this. Thus, if two linearly linked lists are each of length, list appending has asymptotic time complexity of. In the Lisp family of languages, list appending is provided by the append procedure. Many of the special cases of linked list operations can be eliminated by including a dummy element at the front of the list. This ensures that there are no special cases for the beginning of the list and renders both insert beginning and remove beginning unnecessary. In this case, the first useful data in the list will be found at list first node next. Circularly linked list. In a circularly linked list, all nodes are linked in a continuous circle, without using null. For lists with a front and a back, one stores a reference to the last node in the list. The next node after the last node is the first node. Elements can be added to the back of the list and removed from the front in constant time. Circularly linked lists can be either singly or doubly linked. Both types of circularly linked lists benefit from the ability to traverse the full list beginning at any given node. This often allows us to avoid storing first node and last node, although if the list may be empty we need a special representation for the empty list, such as a last node variable which points to some node in the list or is null if it's empty. We use such a last node here. This representation significantly simplifies adding and removing nodes with a non-empty list, but empty lists are then a special case. Algorithms, assuming that some node is some node in a non-empty circular singly linked list. This code iterates through that list starting with some node. Function iterate, some node, if some node are permil null, node, equals some node, do something with node value, node, equals node next, while node are permil some node. Notice that the test while node are permil some node must be at the end of the loop. If the test was moved to the beginning of the loop, the procedure would fail whenever the list had only one node. This function inserts a new node into a circular linked list after a given node. If node is null, it assumes that the list is empty. Function insert after, node new node, if node equals null, new node next, equals new node, else, new node next, equals node next, equals new node. Suppose that L is a variable pointing to the last node of a circular linked list. To append new node to the end of the list, one may do insert after, L, new node, L, equals new node. To insert new node at the beginning of the list, one may do insert after, L, new node, if L equals null, L, equals new node. Linked lists using arrays of nodes, languages that do not support any type of reference can still create links by replacing pointers with array indices. The approach is to keep an array of records, where each record has integer fields indicating the index of the next node in the array. Not all nodes in the array need be used. If records are also not supported, parallel arrays can often be used instead. As an example, consider the following linked list record that uses arrays instead of pointers. Record entry, integer next. Index of next entry in array, integer prev. Previous entry, string name. Real balance. By creating an array of these structures, and an integer variable to store the index of the first element, a linked list can be built. Integer list head, entry records, 1000. Links between elements are formed by placing the array index of the next cell into the next or prev field within a given element. For example, in the above example, list head would be set to 2, the location of the first entry in the list. Notice that entry 3 and 5 through 7 are not part of the list. These cells are available for any additions to the list. By creating a list-free integer variable, a free list could be created to keep track of what cells are available. If all entries are in use, the size of the array would have to be increased or some elements would have to be deleted before new entries could be stored in the list. The following code would traverse the list and display names and account balance. I equals list head, while I permel 0 yen loop through the list, print I, records, I, name, records, I, balance print entry, I, equals records, I, next. When faced with a choice, the advantages of this approach include, the linked list is relocatable, meaning it can be moved about in memory at will, and it can also be quickly and directly serialized for storage on disk or transfer over a network. Especially for a small list, array indexes can occupy significantly less space than a full pointer on many architectures. Locality of reference can be improved by keeping the nodes together in memory and by periodically rearranging them, although this can also be done in a general store. Norvay dynamic memory allocators can produce an excessive amount of overhead storage for each node allocated. Almost no allocation overhead is incurred per node in this approach. Seizing an entry from a pre-allocated array is faster than using dynamic memory allocation for each node, since dynamic memory allocation typically requires a search for a free memory block of the desired size. This approach has one main disadvantage, however: it creates and manages a private memory space for its nodes. This leads to the following issues: it increases complexity of the implementation. Growing a large array when it is full may be difficult or impossible, whereas finding space for a new linked list node in a large, general memory pool may be easier. Adding elements to a dynamic array will occasionally unexpectedly take linear, instead of constant time. Using a general memory pool leaves more memory for other data if the list is smaller than expected or if many nodes are freed. For these reasons, this approach is mainly used for languages that do not support dynamic memory allocation. These disadvantages are also mitigated if the maximum size of the list is known at the time the array is created. Language support: many programming languages such as Lisp and Scheme have singly linked lists built in. In many functional languages, these lists are constructed from nodes, each called a cons or cons cell. The cons has two fields: the char, a reference to the data for that node, and the cdr, a reference to the next node. Although cons cells can be used to build other data structures, this is their primary purpose. In languages that support abstract data types or templates, linked list ADTs or templates are available for building linked lists. In other languages, linked lists are typically built using references together with records. Internal and external storage: when constructing a linked list, one is faced with the choice of whether to store the data of the list directly in the linked list nodes, called internal storage, or merely to store a reference to the data, called external storage. Internal storage has the advantage of making access to the data more efficient, requiring less storage overall, having better locality of reference, and simplifying memory management for the list. External storage, on the other hand, has the advantage of being more generic, in that the same data structure and machine code can be used for a linked list no matter what the size of the data is. It also makes it easy to place the same data in multiple linked lists. Although with internal storage the same data can be placed in multiple lists by including multiple next references in the node data structure, it would then be necessary to create separate routines to add or delete cells based on each field. It is possible to create additional linked lists of elements that use internal storage by using external storage, and having the cells of the additional linked lists store references to the nodes of the linked list containing the data. In general, if a set of data structures needs to be included in multiple linked lists, external storage is the best approach. If a set of data structures need to be included in only one linked list, then internal storage is slightly better, unless a generic linked list package using external storage is available. Likewise, if different sets of data that can be stored in the same data structure are to be included in a single linked list, then internal storage would be fine. Another approach that can be used with some languages involves having different data structures, but all have the initial fields, including the next references in the same location. After defining separate structures for each type of data, a generic structure can be defined that contains the minimum amount of data shared by all the other structures and contained at the top of the structures. Then generic routines can be created that use the minimal structure to perform linked list type operations, but separate routines can then handle the specific data. This approach is often used in message parsing routines, where several types of messages are received, but all start with the same set of fields, usually including a field for message type. The generic routines are used to add new messages to a queue when they are received, and remove them from the queue in order to process the message. The message type field is then used to call the correct routine to process the specific type of message. Example of internal and external storage: suppose you wanted to create a linked list of families and their members. Using internal storage, the structure might look like the following. Record member of a family, member next. String first name. Integer age. Record family the family itself, family next. String last name. String address. Members head of list of members of this family. To print a complete list of families and their members using internal storage, we could write A family equals families start at head of families list, while A family a permil null loop through list of families, print information about family. A member equals A family members get head of list of this family's members, while A member a permil null loop through list of members, print information about member. A member equals A member next, A family equals A family next. Using external storage, we would create the following structures. Record node generic link structure, node next. Pointer data generic pointer for data at node, record member structure for family member, string first name. Integer age, record family structure for family, string last name. String address. Node members head of list of members of this family. To print a complete list of families and their members using external storage, we could write FAM node equals families start at head of families list, while FAM node a permil null loop through list of families. A family equals FAM node data extract family from node, print information about family. Mem node equals A family members get list of family members, while mem node a permil null loop through list of members. A member equals mem node data extract member from node, print information about member. Mem node equals mem node next, FAM node equals FAM node next. Notice that when using external storage, an extra step is needed to extract the record from the node and cast it into the proper data type. This is because both the list of families and the list of members within the family are stored in two linked lists using the same data structure, and this language does not have parametric types. As long as the number of families that a member can belong to is known at compile time, internal storage works fine. If, however, a member needed to be included in an arbitrary number of families, with the specific number known only at runtime, external storage would be necessary. Speeding up search, finding a specific element in a linked list, even if it is sorted, normally requires O(n) time. This is one of the primary disadvantages of linked lists over other data structures. In addition to the variants discussed above, below are two simple ways to improve search time. In an unordered list, one simple heuristic for decreasing average search time is the move to front heuristic, which simply moves an element to the beginning of the list once it is found. This scheme, handy for creating simple caches, ensures that the most recently used items are also the quickest to find again. Another common approach is to index a linked list using a more efficient external data structure. For example, one can build a red-black tree or hash table whose elements are references to the linked list nodes. Multiple such indexes can be built on a single list. The disadvantage is that these indexes may need to be updated each time a node is added or removed. Random access lists. A random access list is a list with support for fast random access to read or modify any element in the list. One possible implementation is a skew binary random access list using the skew binary number system, which involves a list of trees with special properties. This allows worst-case constant-time head-cons operations, and worst-case logarithmic time random access to an element by index. Random access lists can be implemented as persistent data structures. Random access lists can be viewed as immutable linked lists in that they likewise support the same O(1) head and tail operations. A simple extension to random access lists is the min list, which provides an additional operation that yields the minimum element in the entire list in constant time. Related data structures. Both stacks and queues are often implemented using linked lists, and simply restrict the type of operations which are supported. The skip list is a linked list augmented with layers of pointers for quickly jumping over large numbers of elements, and then descending to the next layer. This process continues down to the bottom layer, which is the actual list. A binary tree can be seen as a type of linked list where the elements are themselves linked lists of the same nature. The result is that each node may include a reference to the first node of one or two other linked lists, which, together with their contents, form the subtrees below that node. An unrolled linked list is a linked list in which each node contains an array of data values. This leads to improved cache performance, since more list elements are contiguous in memory, and reduced memory overhead, because less metadata needs to be stored for each element of the list. A hash table may use linked lists to store the chains of items that hash to the same position in the hash table. A heap shares some of the ordering properties of a linked list, but is almost always implemented using an array. Instead of references from node to node, the next and previous data indexes are calculated using the current data's index. A self-organizing list rearranges its nodes based on some heuristic which reduces search times for data retrieval by keeping commonly accessed nodes at the head of the list. Notes. Footnotes. References: 1. Angel. ch20 Euro Data Structures. IDEO 6, Programming with Java PA3 Definition of a linked list. National Institute of Standards and Technology August 16, 2004. Retrieved December 14, 2004, Antonikos, James L. Mansfield, Kenneth C., Junior Practical Data Structures using C++. Prentice Hall PPA 165 Euro 190. ISBN A0-13-280843-9. Collins, William J. 2002. Data Structures in the Java Collections Framework. New York, McGraw-Hill PPA 239 Euro 303. ISBN A0-07-282379-8. Corman, Thomas H. Charles E. Lesserson. Ronald L. Revest. Clifford Stein. Introduction to Algorithms. MIT Press PPA 205 Euro 213 and 501 Euro 505. ISBN A0-262-03293-7. Corman, Thomas H. Charles E. Lesserson. Ronald L. Revest. Clifford Stein. 10.2 Linked Lists. Introduction to Algorithms. MIT Press PPA 204 Euro 209. ISBN A0-262-03293-7. Green, Bert F. J.R. Computer Languages for Symbol Manipulation. IRE Transactions on Human Factors in Electronics, 3 Euro 8 doi, 10.1109/THFE 2.1961.4503292. McCarthy, John. Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. Communications of the ACM3, 184 doi, 10.1145/367177.3671999. Knuth, Donald. 2.2.3-2.2.5. Fundamental Algorithms. Addison Wesley PPA 254 Euro 298. ISBN A0-201-89683-4. Newell, Alan. Shaw, F.C. Programming the Logic Theory Machine. Proceedings of the Western Joint Computer Conference, 230 Euro 240. Parlanti, Nick. Linked List Basics. Stanford University. Retrieved September 21, 2009. Sedgwick, Robert. Algorithms in C. Addison Wesley PPA 90 Euro 109. ISBN A0-201-31452-5. Schaffer, Clifford A. A Practical Introduction to Data Structures and Algorithm Analysis. New Jersey, Prentice Hall PPA 77 Euro 102. ISBN A0-13-660911-2 Wilkes, Morris Vincent. An experiment with a self-compiling compiler for a simple list processing language. Annual Review in Automatic Programming 4, 1 doi, 10.1016/0066-4138, 64, 90013-8. Wilkes, Morris Vincent. Lists and Why They Are Useful. Proceeds of the ACM National Conference, Philadelphia 1964, F1 Euro 1 Shamuga Sundaram, Kulish. Linux kernel linked list explained. Retrieved September 21, 2009. External links, Introduction to Circular linked from the Scanf description from the Dictionary of Algorithms and Data Structures, Introduction to Linked Lists, Stanford University Computer Science Library, Linked List Problems, Stanford University Computer Science Library, Open Data Structures, Chapter 3, Linked Lists, Patent for the idea of having nodes which are in several linked lists simultaneously.